Hello, my name is Tian. I'm a PhD student in computer science at Northwestern University. Today I'm going to tell you about our work, coordinate-based speed of sound recovery for aberration-corrected photoacoustic computer tomography. Photoacoustic computer tomography is an emerging medical imaging modality where ultrasonic waves are created in the tissue by laser stimulation, and an array of transducers around the tissue will collect those ultrasonic signals, which will be eventually fed into an algorithm to reconstruct an tomography image of the tissue, usually called the initial pressure image. If the speed of sound that the ultrasonic wave travels inside the tissue is a constant, a very cheap back projection algorithm can easily reconstruct a clean initial pressure image. However, that is not the case in reality. In reality, speed of sound distribution varies, which will create distortions in the wavefront, which will eventually lead to aberrations in the reconstructed image. In this work, we propose to jointly reconstruct the speed of sound distribution and the initial pressure image so that we can use the aberration information encoded in the speed of sound distribution to remove the artifacts in the initial pressure image. Here is an overview of our method. We first feed the ultrasonic signals we collected into a conventional back projection algorithm, namely the DAS algorithm. We choose several different delay distances to generate an image stack and crop the image stack into patches. We then feed those image patches into a patch-wise multi-channel deconvolution module. On the other branch of our method, we parameterize the speed of sound distribution with coordinate-based representation, either a pixel grid or a neural field, and calculate the spatial varying PSF stacks corresponding to the delay distances used in the DAS image stack, assuming a straight acoustic ray model. And then we feed the PSF stacks into the deconvolution module to solve for a deconvolved initial pressure image. Eventually, this initial pressure image will be fed into a loss function consisting of a data fitting term and a regularization term. We optimize for the parameters of the speed of sound representation, and after we obtain the speed of sound distribution, we calculate the spatially varying PSFs and remove the artifacts in the initial pressure image with deconvolution. Note that our method is trained at test time on a single measurement. That means our method is free from large training dataset and it's self-supervised. We demonstrated our method on both numerical data and real-world data. In this numerical experiment, we create the following numerical phantom with a customized initial pressure and speed of sound distribution. We first picked a location marked by a white X in the speed of sound distribution and look at the wavefronts reconstructed by several methods. We are able to show that the wavefront captured by our method, denoted in purple and blue corresponding to different types of coordinate-based representations, matches the best with the actual wavefront, denoted by the black line in this plot. We then compare with conventional DAS, dual SOS DAS, APAC'd in terms of reconstructed image quality of the initial pressure distribution and the speed of sound distribution, and we're able to show that our method is able to produce the best performance in both images while being very efficient. We then show our results on a leaf phantom, where we put a leaf into a piece of gel, which has a hole that is filled in water to create the non-uniform speed of sound distribution. We show that our method correctly reconstructs the speed of sound nature of the dual-body leaf phantom, where in the middle, the speed of sound of the water is smaller, and in the periphery, the speed of sound of the gel is larger. Eventually, we test our method on an in vivo mouse liver data, where we are able to show that our method correctly reconstructs fine details in the initial pressure image, for example, blood vessels and bones, and correctly captures the liver structure in both the initial pressure image and the speed of sound distribution. This can be shown in the overlaid image of the initial pressure and the speed of sound on the right, where the boundaries of the liver structures in both images overlaps really well. In summary, we introduce a self-supervised framework for joint reconstruction of speed of sound and initial pressure impact. We're able to show that our method produces the best speed of sound PSNR and initial PSNR compared to all other methods. We demonstrate the effectiveness of our method on numerical simulation and real-world data. We highlight the interpretability and scalability of our method coming from its physics-based, self-supervised nature. Thank you for watching. Feel free to scan this QR code to check our project page for more details.